Right now we have to move on to Dr. Aidala. So thank you again. And let me just now spotlight Dr. Aidala. Thank you, Dr. Holds. Okay. My Wi-Fi is a bit flaky, so all right. Awesome. Kailash, you can take it away.
Thank you. Dr. Christine Aidala is a professor of physics at the University of Michigan and a researcher in the field of high-energy nuclear physics. Her research primarily focuses on quantum chromodynamics, analyzing the theoretical strong nuclear force between the fundamental particles that make up protons and neutrons. She works in a large-scale experiment at the relativistic heavy ion collider in Brookhaven National Laboratory, named Phoenix, investigating the interaction between protons and heavy ions. Dr. Aidala is a recipient of the 2015 Sloan Research Fellowship, as well as the 2015 Career Award from the National Science Foundation, and is here to speak today about even smaller components of protons, which are quarks and gluons. Thank you, Dr. Aidala, for coming here. We appreciate it.
Yes, thank you. So we've been hearing about very large distance scales, cosmological distance scales across the universe. Now we're going to switch to very, very small distance scales, as my research focuses on the internal structure of the proton. So protons are a fundamental building block of everyday matter. Every single atom and all of the everyday matter in the world around us is made of or includes protons. Here I show just simple schematic diagrams of two elements, an atom of hydrogen, an atom of carbon. The proton, we can look at the hydrogen atom. Proton carries a +1 electrical charge. This is counterbalanced by the -1 electric charge of the single electron. We go to a carbon atom as another example. We have 6 protons balanced by 6 electrons. We also have in the nucleus of a carbon atom 6 neutrons, which are very similar to protons in many ways, but they're electrically neutral, which is why they're called neutrons. So how did we first discover the nucleus of an atom? Well, we've got to go back a little more than 100 years. So there was a series of experiments done in Manchester, England between 1908 and 1913 by Ernest Rutherford, Hans Geiger, and Ernest Marsden. You might have heard of Geiger's name before because the Geiger Counter is named after him. It's a device used to detect particles from radioactive decays. What they did was they scattered something known as alpha particles, which were produced in the radioactive decay of the element radium. They scattered them off of a thin gold foil. So think aluminum foil, just a little bit more expensive and harder to buy in the supermarket. So alpha particles are charged. They have +2 electrical charge. And what they saw when they did this experiment with the alpha particles, going through the gold foil, most of them went through and were only deflected just a little bit. And this actually was consistent with the hypotheses of the atomic structure of the time. The most popular hypothesis about atomic structure at the time was known as the plum pudding model. It said that the positive and negative charge centers inside an atom were distributed approximately evenly over the volume of the atom. And so if you have a positively charged alpha particle passing through a gold atom, then okay, it would have some positive charge centers nearby, but also some negative charge centers nearby. And it wouldn't get repelled too much or attracted too much. It would just get deflected by small angles. However, I think this is a nice illustration of how important it is to repeat your experiments. They did this tens of thousands or hundreds of thousands of times. And what they saw was that about 1 in 8,000 bounced off at a sharp angle. So maybe at a right angle or even back toward the beam direction. And this was a surprise at the time. What it said was that the electric charge centers, the plus and minus charges in an atom, were not equally distributed over the volume of the atom, but in fact, there was a positively charged core at the center. So when the positive alpha particles came in, most of the time, because this was concentrated all at the center of an atom, most of the time they didn't come that close, and so they were only deflected at these small angles. But the times when they did come close to that positively charged core, which we now know to be the nucleus, they were repelled very strongly. and could bounce back at sharp angles. And so now if we just think of the size of the nucleus relative to the size of an atom, just rounding to powers of 10, I'm going to round this 1 in 8,000 to about 1 in 10,000, right? So the size of the nucleus is only about 1/10,000th of the size of an atom. This is why about 1 in 10,000, 1 in 8,000 of these alpha particles went nearly straight through. They were using gold foil. So gold has a total of 197 protons and neutrons in the nucleus. So now if we think of the size of a single proton, just the nucleus of a hydrogen atom, this is going to be even smaller. So it's about 1/100,000th of the size of an atom. In terms of meters, we heard a lot yesterday about nanoscale science, 10 to the minus 9 meters. Now we're a million times smaller distance scales, about 10 to the minus 15 meters or 1 femtometer. So the radius of the proton is about 0.8 times 10 to the minus 15 meters. So we skip ahead a little more than 50 years, and now they were doing very similar experiments, with different people obviously, very similar experiments at the Stanford Linear Accelerator Center in California. A very similar idea to those Rutherford, Geiger, Marsden experiments from the early 1900s. They scattered electrons off of protons, and they saw that many bounced back sharply. And they, just using conservation of momentum, they saw that those scattered electrons were not bouncing off the whole proton, they were bouncing off of some kind of subcomponents. So this revealed that protons were not solid lumps of positive charge. They had some kind of constituents, and we now call these constituents quarks, as has been mentioned by a couple of speakers today as well as yesterday. And if you're interested in learning more about particle and nuclear physics, I have this website here, particleadventure.org, which I would highly recommend. So the simplest model of the proton is 3 quarks, 2 up flavored quarks and 1 down flavored quark. Flavor is a property of subatomic particles that's related to the weak nuclear force and radioactive decays. I'm not going to be talking more about that here. But these quarks inside the proton are not completely free. They are bound by force carrier particles, which are called gluons. And gluons are, in fact, named after glue because they stick, they bind the quarks together inside the proton, also inside neutrons. There's also something known as C-quarks that are present inside the proton. These are short-lived quark-antiquark pairs that come out of quantum mechanical fluctuations, sort of whipping in and out of existence. And this little table here shows the 6 types of quarks, 6 flavors of quarks. So the up and down are the ones that are most relevant to the proton as well as the neutron. The next one that was discovered came as a surprise and was called strange. By the time the charm quark was discovered, people had predicted it, so they were feeling pretty happy with themselves. This wasn't a surprise, and they gave it a more positive name, let's say, charm. And then the heaviest 2 are known as top and bottom. So if you think about it, an atomic nucleus is made of protons and neutrons. Heavy elements have a lot of protons, and we know that the protons are all positively charged, and the neutrons are electrically neutral, so they're not canceling out that positive electric charge. The electromagnetic force should cause those protons to repel one another. And it is causing repulsion. However, the strong nuclear force is overcoming this repulsion. Protons and neutrons interact via the strong nuclear force carried by these gluons. And the strong nuclear force is much stronger than the electromagnetic force, about a factor of 100, and about 10 to the 38 times stronger than gravity, so thus the name. However, it has a very, very short range of about 10 to the minus 15 meters. So this is a key difference. We'll come back to that in a minute. First, let me talk about what kind of charge particles need to have to interact with the strong force. So the strong force acts on particles that carry what's known as color charge. So quarks carry color charge, plus gluons themselves carry color charge. So if this is in contrast to electromagnetism. So in electromagnetism, you can have electrically charged particles that attract or repel if they have the opposite signs, like signs. And this repulsion or attraction is transmitted via exchange of photons, so the particle manifestation, particle form of electromagnetic waves. The photons themselves, though, do not carry electric charge. They are electrically neutral. So in the strong interaction, the gluons, which are the force carrier particles that are similar to the role of similar to the role of photons in electromagnetism, these gluons also carry charge, color charge in this case, strong force charge. So why is it called color? It's not something we can see. And it's called color because back in the 1970s, when people were first understanding the strong nuclear force, they saw that you needed 3 different charges to make a neutral particle. So if you compare this to electromagnetism, there are just 2 different types of charges, 2 different types of electric charges, which we call positive and negative, or plus and minus. When we combine those, they make an electrically neutral particle. For the strong force, they saw you needed 3 different charges to make a neutral particle. And they thought, well, what should we call them? And they thought of red, green, and blue light combining to make color neutral white light. And this is what led them to call this type of charge color. And so the theory, the quantum field theory describing the strong nuclear force is known as quantum chromodynamics, with this chromo referring to color charge. Note that quarks also carry fractional electric charge, which I think is probably something very deep that we have not understood yet. So I told you that the proton is made of 2 up quarks and a down quark. So up quarks actually carry positive 2/3 electric charge, and down quarks carry minus 1/3. So we have plus 2/3, plus 2/3, minus 1/3, gives us a total of 3/3, so plus 1 charge of the proton. The neutron instead is made of 2 down quarks and an up, so minus 1/3, minus 1/3, plus 2/3 gives us our electrically neutral neutron. So we actually never see quarks or gluons directly, and this is something very special about the strong force that gives us a lot of rich things to study, but also can complicate our lives and create some challenges as well. So the quarks and gluons are always confined to composite color neutral particles. They can either be in groups of 3 quarks, so in any instant, one of them would be red, 1 green, and 1 blue. The gluons are always being exchanged between those quarks, so you wouldn't say, oh, the down quark is the red quark. It's exchanging gluons, and the gluons actually can change since they carry color themselves. They can swap the color of a quark, but in any given instant, in say a proton or a neutron, one of those quarks is red, 1 green, and 1 blue. These are called baryons. Bary is a Greek root meaning heavy, the heavy particles made of quarks. They can also come in groups of 2, so a quark-antiquark pair, where in any given instant, the quark is carrying a color and the antiquark is carrying the corresponding anticolor. And these are called mesons, or middleweight particles. If you do try to pull 2 quarks apart, the energy between them increases until you produce a new quark-antiquark pair. This is through the famous equation E = mc². And I like to think of this as an elastic band. So if you are pulling apart an elastic band, then the farther you pull, the more force there is trying to pull you back. And so this is similar to the strong force. And as you're pulling farther, you are storing more and more potential energy in that elastic band. And at some point in the case of an elastic band, that energy stored, potential energy stored in the elastic band is gonna lead to the band breaking. So if you try to pull 2 quarks apart, then we have energy between them carried by gluons, or a gluon field. And at some point, that potential energy stored in the gluon field can create a new quark-antiquark pair. We're changing this potential energy into a new massive particles through E = mc². And then those new the new quark and antiquark will go and bind with the original ones, forming the particles that then I can observe in my detector. So always these bound states with quarks inside them, never a free quark. So if you can't see individual quarks and gluons, how do you determine the proton structure? Well, in general, what we do is we do inelastic scattering. We shoot a high energy beam, for example, of electrons at the proton to break it up, and we try to understand what happens. The electron exchanges a photon with a quark because quarks carry electromagnetic charge, remember that fractional electromagnetic charge, as well as color charge. Electrons do not carry color charge. And so it's the only way that an electron can interact with a quark is because the quarks do carry this fractional electromagnetic charge. So if we look at this diagram, here we have an electron beam coming from one direction, a proton beam coming from another. Here I've tried to just sort of schematically indicate the simplest picture of a proton with these three quarks. So what we're going to do is we are going to break up this proton. So it's inelastic scattering with a proton. However, it's going to be elastic scattering with one of the quarks inside it. Because it's elastic scattering with one of the quarks inside it, we can actually use conservation of energy and momentum to infer information about the quark in the instant when it's scattered from within the proton, just by measuring what happened with where the energy and angle of the scattered electron. So in general, if we're trying to measure what's inside the proton, I said the proton radius is about 0.8 times 10 to the minus 15 meters. We are going to need to go to very high energies to see to probe such small distance scales. So if you think of the electromagnetic spectrum from radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays, these all correspond to different wavelengths and different energies. So we're increasing in energy going from left to right on this diagram, and the higher energy corresponds to smaller wavelengths. So if you think about using an optical microscope, something you might use in a biolab, you can use optical light, just regular light, to see microbes, protozoans, bacteria. And that's because the wavelengths of visible light, which are about 0.5 microns or 500 nanometers, about 400 to 700 nanometers, are small enough to resolve the features of those distance scales. If we want to study molecules, atoms, atomic nuclei, protons, and inside of protons, we're going to need to go to smaller wavelengths and therefore higher energies. So as was already mentioned in some talks yesterday, we can study the molecular structure of matter using ultraviolet light. Ultraviolet light has wavelengths of about 10 to 400 nanometers. So this corresponds to molecular distances. If we want to study atomic structure, we got to go a little bit smaller and a little bit higher energy to X-rays, where the wavelengths are about 0.01 to 10 nanometers. Now I want to go to nuclei and protons. Remember we said that 1 in 8,000 bounced back in that original Rutherford scattering experiment. So we're rounding to 1 in 10,000. So if I want to study nuclei, I'm at a distance scale of 10,000 times smaller than studying an atom. If I want to study just a proton, I'm about 100,000 times smaller than an atom. So what we need to use are high energy particle accelerators to see inside them. And we'll be taking advantage of something called wave particle duality in quantum mechanics, which Professor Terry Odom actually mentioned in her talk yesterday. And in just one sentence summary, what the internal structure of the proton looks like depends on what energy scale you probe it. So that what energy scale is going to correspond to the distance scale. So if you are using low enough energies, long enough wavelengths, you're going to see basically the proton as a whole object. At intermediate, so slightly shorter wavelengths, slightly higher energies, you're going to be able to resolve this 3-quark structure of 2 up quarks and a down quark. And if you go to much higher energies, corresponding to much smaller wavelengths, you're going to be able to resolve this quark-anti-quark structure, these quark-anti-quark pairs fluctuating in and out of existence. So let me switch gears and talk about my experiment. So I work at the Phoenix experiment at the Relativistic Heavy Ion Collider at Brookhaven National Laboratory on Long Island, New York. And I'm part of the LHC Beauty Experiment at the Large Hadron Collider at CERN in Geneva, Switzerland. This facility goes across the French-Swiss border. You can just see the Geneva airport right near the Large Hadron Collider Beauty Experiment. So the Relativistic Heavy Ion Collider is the only active collider in the United States. This is a satellite photo, and you can see this ring here. It's not the accelerator beam pipe. We don't have it out in the elements. This is the road that drive to the different buildings and facilities along the 2.6 mile, 3.8 kilometer circumference ring. This is New York City here, Manhattan, Brooklyn, Queens. It's about an hour and a half east of New York City. And here's an aerial view. By 2030, so relevant for any of you who might be interested in going into nuclear or particle physics, this will be transformed into a brand new facility known as the Electron Ion Collider. All of my work, because it requires these very large accelerator facilities, these are done at national and international scales, not at single universities. These aren't tabletop experiments. You have things that are multi-kilometer, multi-mile scales. And so even though we're 10 years before first data is expected from this brand new facility, the Electron Ion Collider, we already have 238 institutions from 32 different countries that have said they want to be involved and that are getting involved in the design work that's going on right now. So the relativistic heavy ion collider is actually a great place to work if you want to study protons in the strong force. We're studying several different systems, strong force systems, so protons, of course, this is my focus. And we have the ability to polarize, to control the spin direction of the proton beams there. This is a completely unique capability of this facility worldwide. We're also studying nuclei, and nuclear matter is so hot and dense that the quarks and gluons are briefly deconfined in what's known as a quark-gluon plasma. We have two colliding beams going in opposite directions around the circle of ions, ranging from hydrogen, so protons, through uranium nuclei. And the facility is called the Relativistic Heavy Ion Collider because people were concerned that residents in the area would be very concerned if they had a nuclear collider, since people sometimes get nervous about nuclear physics. But these ions have all the electrons stripped off the atom. So we run a lot with gold beams, for example. This is gold plus 79, so it's not really a chemist's ion. The Relativistic Heavy Ion Collider has been running since the year 2000. It involves about 1,000 scientists coming from universities and laboratories around the world. The detectors are sort of building size, the scales of these. You can see a person working on the Phoenix detector while it's opened up for maintenance. Here's the beam line where one of the beams come in and the other as it passes out. They're going opposite directions through this single beam pipe. About 4 stories tall, 40 feet long, about 3,000 tons. We have different detector subsystems for measuring different kinds of produced particles or different information about them, such as electric charge, momentum, energy, or particle type. The Large Hadron Collider over in Geneva, near Geneva. Again, here's the airport. It's been running since 2010. It involves about 10,000 scientists total from around the globe collaborating on the 4 experiments. In terms of the data volume, the whole facility is collecting about 90 petabytes per year. So this is not something you study with pencil and paper. It's very computationally intensive. The Large Hadron Collider Beauty Experiment, I didn't tell you before, but the top and bottom flavor quarks, some people prefer the more poetic terms, truth and beauty. So my colleagues insist that this is not the LHC bottom experiment, it is the LHC beauty experiment. It's optimized to study the beauty quark. And here I show you just a visualization of a proton-proton collision. These are the particles or representations of the particles came out and what we measured in the different parts of the detector. This produced what's known as a Z boson. This decays to 2 muons, which are these 2 green tracks here. And then there's a quark jet, which sort of looks like these almost twisted black lines, or these different particles produced by a high energy quark. Remember, we said that you can't just see the quark by itself. If I have a really high energy scattered quark, it's going to produce many particles, and that's what this cluster of particles is here. The Large Hadron Collider is about 100 meters underground. So our detector is about 100 meters below the French countryside. We look at we record about 10 million proton-proton collisions per second. It also has beams of protons like the Relativistic Heavy Ion Collider, but we cannot control the polarization, the spin direction. And for a few weeks a year, this facility runs nuclear beams also. However, the collider runs at higher energies than the Relativistic Heavy Ion Collider because the focus is on searching for new particles rather than studying the proton and the strong nuclear force. And here you can see a photo from this past November. I got to go with my kids down to underground to the experimental hall, which was great to be able to go together. So before I have just one slide on my path, I just want to offer thanks to my group members, my postdoc, PhD students, undergrads, and visiting scholars, as well as acknowledge the the Department of Energy and National Science Foundation for funding my work. A few words on my path from high school. So for high school science and math, I took AP Physics B. My high school didn't offer a calculus-based AP Physics. I took AP Bio, AP Calc BC. We had both AP Calc AB and BC, but my high school at the time didn't have AP Chem or any other AP Science or math courses. I was in the math club. I was a mathlete from 7th grade on. So I was definitely interested and involved in math already in middle school and high school. I went on to college. I double majored in physics and music. I now get to teach a course on the physics of music at the University of Michigan, which has been really nice to draw on some of my music background in my job as a professor of physics. I didn't get involved in research until the summer after my freshman year in college. So I didn't have any opportunities like that in high school. So if you're not in a position to have such opportunities, you really shouldn't worry about it, but definitely try to find ways to get involved in college. I worked in an experimental nuclear physics lab on campus. So this really, it seemed interesting to me, and the professor had an opening. So this was how I got involved in experimental nuclear physics. That first research advisor suggested I apply to summer programs at national labs. So after sophomore year of college, I ended up getting an internship working at the relativistic heavy ion collider at Brookhaven National Lab more than 20 years ago now. And that was what sort of launched me into this field, although I did a few different things in nuclear and particle physics for a few years in between before coming back to it. And there is a program, it's got a different name now than when I did it, but the Department of Energy Science Undergraduate Laboratory Internship Program open to undergraduate, to college students interested in science to do summer and also semester programs at, I think, 17 different national labs in the United States. From there, I continued in experimental high energy nuclear and particle physics, doing other research projects during college, and then pursuing a PhD in physics. So just a summary, even though protons are a fundamental building block of everyday matter, we still have lots to learn about the complex behavior of the quarks and gluons inside them. High energy particle accelerators are tools that allow us to probe the structure of very tiny objects. So in my case, I'm probing distance scales less than 10 to the minus 15 meters. And there's a community of a few thousand people around the world that's working to unravel the mysteries of the proton and the strong nuclear force that holds it together. Thank you.
Thank you so much, Dr. Aidala. Does anyone have any questions for her before we start physics competition? Okay, let me check out the YouTube. Oh,
I can see the chat. Did you do a performance education major in music? So it was actually a general music degree. So my university had a music school, but it was a graduate music school. So for undergraduate degrees, it wasn't a Bachelor of Musical Arts. It wasn't a performance degree. So I had performance credits, but it was a general music degree.
I have one question. Which one, or what has been your favorite research project out of all of the ones that you've done?
That's a good question. Probably, I guess it's even hard to define a project. I mean, I think I've really enjoyed working with the Phoenix experiment. I've actually, these are long-term experiments. I've been on it for 19 years now. And I think what was really exciting about that in particular was discovering for the first time in 2014 that the gluon spins contribute to the total spin of the proton. That had been there's still aspects of proton polarization and proton spin that remain a puzzle, but that was a big announcement in 2014 that the gluons are contributing. So that was definitely a highlight of my time working with the Phoenix experiment at the relativistic heavy ion collider. Another thing is, it's not really a project, but in general, one of the aspects I like about working in high energy nuclear and particle physics at these international facilities is really the international aspect, the international cooperation aspect, the fact that I get to work on a daily basis with colleagues from all over the world, which when the pandemic started, emailing my colleagues in Wuhan to ask them how they were doing, just made it feel really different than if I hadn't been working with people from that particular city even. And there have been a lot of things over the past 20 years that have come up with world events where it's been interesting and really eye-opening to be able to talk directly with people who are living and working in these different regions of the world. My data, I see, hang on, let me scroll up in the questions. How do the detection instruments work? Do they actually view the particles in their paths, or do they hypothesize, like, guess them? So different types of detectors get different information about the particles. So for example, charged particles can ionize a gas. Like if I have a charged particle passing through regular gas, it'll knock off some electrons, and then we can collect those electrons and we say, aha, a particle passed right near here, because I see that some electrons got knocked off. We can also, charged particles also bend in a moving charged particles bend in a magnetic field, and the radius of curvature in that magnetic field gives us information on their momentum. So they view the particles, but not in the sense of with our eyes. We're collecting, charge, electrons knocked off the atoms. So there's this really clear signature that we collected those ionization electrons. But you're not seeing it with your eyes. You're then reading charge out of an instrument to say we collected some electrons. Another question is, what is your day-to-day work life like? So I spend a lot of time, I'm a university professor, so some of my time is teaching undergraduate and graduate courses. I spend a lot of time with my research group members, mentoring graduate students on different research projects, and on undergraduates as well. I've had a few high school students over the years that have worked on some hands-on detector development projects in my laboratory. And so I've had a neutron detector development project for like a new way of detecting neutrons using liquid argon, for example, and that's on campus at the University of Michigan, even though my accelerator facilities are all off campus. And I spend time going to take shift for maybe a week or so at a time, or going to collaboration meetings and going to different conferences. My PhD students will go for months or years at a time to the experiment, typically. Another question is, how well is it to get grants these days, better or improving? So I guess I've been mostly fortunate, at least, in being able to get financial support to do my research. So most of the financial support I get directly is to pay the salaries of the researchers working in my group, and to travel to the experimental facilities, because we need to travel to go to the experiments. So, and then to travel to talk about the work at scientific conferences around the world. So I think it's been okay for me. It's actually really exciting that the Electron Ion Collider was just announced as a new project approved by the government about 6 months ago.
Thank you so much, Dr. Aidala. We're going to start the physics competition soon. So I think that was the last question, but I hope everyone really enjoyed the physics talks. I know I really did, even though, I'm like more the biology side. Yeah, all of the physics speakers were so awesome. So thank you all, and thank you, Dr. Aidala.